Picture this. It's 1928, and a young, super-assuming physicist shuffles onto a stage in Germany. He's presenting his latest work, speaking with this incredibly detached rhythm, honestly showing absolutely no sign that he's even enjoying his own lecture. But the math he starts writing on that chalkboard, it was about to send some of the most brilliant minds of the 20th century completely spiraling. I mean, Werner Heisenberg, an absolute titan of quantum mechanics, was so devastated by what he saw that he literally called it the saddest chapter in modern physics.
It really was like watching a documentary-style mystery unfold in real time. Heisenberg actually wrote to Niels Bohr saying he was acting out of pure despair and had taken up another field entirely. There's even a legend that Wolfgang Pauli announced he was abandoning physics altogether just to go write utopian novels. No way, right? So what on earth did this young man say to disrupt quantum mechanics so profoundly? Well, he had discovered something deeply, deeply troubling hidden inside the math, a concept of negative energy, and it seemed to break reality itself.
Welcome to This Explainer, where we are going to track the intense, historical detective work that drove the greatest minds of the 1920s right to the brink. It's a wild journey that began as a solitary quest for mathematical beauty and somehow ended up accidentally predicting the existence of antimatter. Let's dive right in.
Section 1. Quantum meets relativity. To really grasp this crisis, we have to visually look at the massive problem physicists were facing back in the 1920s. On one side, you had Schrödinger's wave equation, right? Brilliant for slow-moving particles. But at high speeds, the math literally distorted reality. It falsely predicted that heavy, fast-moving elements like gold would be a dull silver gray, and liquid mercury would just freeze solid. On the other side, you had Einstein's special relativity, which perfectly ruled the high-speed universe near the speed of light. Physicists desperately needed a mathematical bridge to fuse these two colliding worlds together.
So, in 1926, right after Schrödinger published his work, Oscar Klein formulated a relativistic update. He essentially took Einstein's energy-momentum relation and just kind of jammed it into the quantum wave operators. Two other physicists independently figured it out too, so it became known as the Klein-Gordon-Fock equation. And you know, the great Niels Bohr actually thought this had fully solved the issue. He even brushed off younger physicists, telling them the problem was already fixed.
But here's the thing. The Klein-Gordon equation had fatal mathematical flaws. By squaring the energy operator, they accidentally introduced a second-order time derivative. And what does that mean? Well, it meant that to predict a particle's future, you needed to know its exact starting point and its velocity simultaneously, which is a strict violation of quantum uncertainty. And worse, it birthed negative probabilities. Imagine looking inside a closed box and having a less than zero chance of finding a particle inside. It was literal physical nonsense, and the community brutally rejected it.
Section 2. The matrix solution.
Enter Paul Dirac. This guy was a man of so few words that his colleagues literally invented a unit of measurement called the Dirac, defined as speaking exactly one word per hour. Dirac was famous for climbing trees in full three-piece suits, and he treated physics like this elaborate, beautiful game. He was deeply drawn to Einstein's relativity purely because of its deductive mathematical elegance. Dirac absolutely insisted on finding a linear equation, one without those messy squared time derivatives that cause those negative probabilities. He wanted absolute mathematical beauty, even if it didn't perfectly fit the experiment at first.
So, Dirac writes out this beautiful linear equation. But to balance Einstein's rules, he had to assign coefficients to the momentum. Here's where things get crazy. When he set up the simultaneous equations, normal everyday numbers completely failed. He needed a mathematical object where multiplying a times b yielded a completely different result than multiplying b times a, which, violates the most basic rules of algebra. With standard numbers, 2 times 3 is always exactly the same as 3 times 2, so he was totally stuck.
But then, his stroke of genius. He realized he didn't actually have to use regular numbers, he could use matrices. Inspired by his highly outgoing friend Werner Heisenberg's use of non-commutative matrices and the uncertainty principle, Dirac applied them right here. But a simple 2x2 matrix just wasn't enough to visually capture the sheer complexity of spacetime, so he mathematically ripped open the dimensions, expanding his equations into a massive 4x4 grid to make the whole shebang balance perfectly.
Section 3. The negative energy crisis.
Because that 4x4 matrix is exactly what broke the minds of the scientific community. It output 4 distinct states for an electron. Now, the top 2 states magically predicted electron spin, spin up and spin down, which perfectly solved lingering mysteries like the split emission lines in a hydrogen atom. But the math also demanded two extra states, solutions where the absolute energy of the electron was a negative number.
This right here is exactly why Heisenberg called Dirac's theory a tragedy. Think about it. If an electron could truly possess negative energy, what was stopping a regular electron from violently radiating away its positive energy in a blinding flash of light and just plunging endlessly into lower and lower negative energy states? Nature would literally become an infinite cascade of electrons violently falling into a bottomless negative abyss until reality itself unraveled. It seemed like pure, absolute nonsense.
Section 4. The discovery of antimatter.
For 3 long years, Dirac stubbornly stuck to his beautiful math, even as his peers practically begged him to abandon it. Finally, in 1931, he proposed an unimaginably radical idea to explain away those negative numbers. He suggested they were actually describing an entirely new, undiscovered particle. It would have the exact same mass as an electron, but a positive charge, the anti-electron. And you know what happened? When he published this, the physics community essentially ignored him. Nobody started running around looking for anti-electrons.
Fast forward just 1 year later, a Caltech postdoc named Carl Anderson was studying cosmic rays in a cloud chamber. He accidentally captured a physical impossibility, a track that looked exactly like an electron, but in the magnetic field, it violently hooked in the totally opposite direction. It couldn't be a heavy proton because of how incredibly far it traveled through the air. It was light, fast, and positively charged. Anderson had discovered the positron. Dirac's wild chalkboard math had actually predicted physical reality.
But they still had to fix that pesky negative energy bug in the math. A brilliant trick was eventually pieced together by Ernst Stueckelberg and Richard Feynman. Because the math multiplies energy by time, Stueckelberg realized you could mathematically flip the arrow of time itself. Feynman famously visualized this in a way that just blows your mind. A negative energy electron tumbling backwards through time is mathematically identical to a piece of positive antimatter flying forwards into the future. Boom! The math was saved.
Section 5. The Big Bang Finale. Jumping from the chalkboards of the 1920s to the very origin of our cosmos, we can really see the massive existential consequence of Dirac's discovery. For every particle, there is an antiparticle. When matter and antimatter touch, they don't just bump into each other. They annihilate completely, vaporizing instantly into blinding, pure photons. In the first fractions of a second after the Big Bang, our universe was this hyper-dense, violently boiling soup of matter and antimatter constantly popping in and out of existence. Logically, they should have flawlessly annihilated each other, leaving behind a cold universe of absolutely nothing but pure, glowing light. But obviously, we are here. Working backwards from the cosmos we see today, physicists estimate that out of that intensely violent early universe, only 1 in a billion matter particles survived the Great Annihilation. Just think about that, 1 in a billion. And those microscopic leftover survivors went on to form literally everything in our universe today. You, me, the stars, the planets, all of it, from a microscopic rounding error in the cosmic math.
Oh, and as a fascinating, very human footnote to this whole story, the impossibly silent, emotionally detached Paul Dirac actually ended up marrying Margit Wigner, the sister of his colleague. She was incredibly empathetic and incredibly talkative. As a friend noted, he gave her status, she gave him a life. I guess it's proof that sometimes in nature and in life, antiparticle personalities actually do attract and survive without annihilating each other.
But that leaves us with the ultimate question of our existence. If matter and antimatter are perfect opposites, what allowed that single matter particle per billion to escape the fires of annihilation and build our entire world? Why did matter win? That profound physical asymmetry is a mystery physicists are still desperately trying to crack today. It really makes you realize just how incredibly lucky we are to be here, floating in a universe that, mathematically speaking, perhaps shouldn't even exist. Until next time, keep questioning the universe around you.